at electronegativity values and how they predict the type of bonding that you have in the compound. So in other words, is the compound an ionic or covalent compound? So you see I photocopied this or photographed it from your revision book, okay? So you see the value here, it's on page 38 of your revision book in case you need it for something, or when you're having a look at it. So here you can see, look, that if there's no difference in electronegativity values, then your compound is pure covalent. What does that mean? Well, if you've got a bond there formed between two atoms A and B, then you know the electrons are being shared equally. Right in the middle, equal sharing. You would have no regions of positive and negative here. Pure covalent, or we would say it's not polar, non-polar, okay? If the values then, when you subtract, are greater than 0, but less than 0.4, you say that it's negligible, that there's negligible polarity there. So really and truly, it'll kind of behave the same as a non-polar molecule. Okay, so there's negligible polarity, very little polarity there. More or less, you can say that it's pure covalent, non-polar. Look, if it's greater than 0.4 but less than 1.7, it's polar. Now, what does that mean? Well, if you have a bond AB, whichever atom is more electronegative. So say the B is more electronegative, then the electrons will go closer to B, making it slightly negative, and this A atom will be slightly positive. Polar bond there, okay? And then if your difference is greater than 1.7, then the compound is ionic, okay? So that'll help you to determine if the bonding is covalent or ionic. All right. Now, I just want to show you this way here for a second now. And you see here, now obviously I just wanted to show you this there so that you'd see the table of electronegativity values, and you know that that's in your logbooks, okay? You don't need to remember those values. So you use the table of electronegativity values. Now look over here, right? They're doing out some examples. If you're asked to predict the type of bonding here between the hydrogen and the oxygen atoms in water. Look up hydrogen's value, it's 2.2. Oxygen's value is 3.44. And when you subtract, you're getting a 1.24 difference in electronegativity value. And that falls within the greater than the 0.4, but less than the 1.7. So that's polar covalent, okay? There is slightly negative oxygen and slightly positive hydrogens in that molecule. If you look at the HCl then, same thing. Look, when you subtract the differences, it falls within that polar covalent category. Greater than 0.4, but less than 1.7. Look at this one. Less than 0.4. So we'll take it that that's not polar. And that's methane. That's one of the molecules that we would have talked about. It's an alkane, not polar. What type of intermolecular bonds did we say? Van der Waals, that sort of thing. So there is no slightly positives or slightly negatives there for that, okay? Just for a second, if you had something like, KCl, we know is ionic. Chlorine is 3.16. The K is 0.82. When you subtract, you are getting greater than 1.7. So you know that's ionic then, okay? Now, the other thing that we would use electronegativity values for is predicting whether a liquid is going to be polar or non-polar. So say I put something into the burette and I don't know if it's polar or if it's not polar. Now just remind yourselves, what does polar mean again? Polar means that there will be regions of positive and regions of negative separated by some distance in the molecules. Now you've water in here, and we've said from the previous slide that water is polar, that there is slightly negative oxygens and slightly positive hydrogens. So if you bring a charged rod to a thin stream of water, then if the rod is negatively charged, the positives in the water, the positive hydrogens in the water would be attracted to the rod. If the rod was positively charged, the negatives in the water, the negative oxygens, would be attracted to the rod. But look in the third example here, cyclohexane straight. Why does cyclohexane not attract towards a negatively charged rod? Because it's not polar. It's non-polar. There are no regions of positives and negatives in cyclohexane, and therefore it doesn't matter if you brought a positive or a negative rod to that stream of cyclohexane, you will not get attraction. Is that okay? So that's that electronegativity thing there. Now, on the show me board now, I just want to do out maybe just one or two examples. So 2008 question 5. Part A, they asked you firstly to define electronegativity. So you know the definition of that is the relative attraction that an atom has for what? For a shared pair of electrons in a covalent bond. And then they asked you in part C to use electronegativity values to predict the type of bonding in water, in methane, and in magnesium chloride. Okay, so what you would do is you'd go to your electronegativity table, you'd find that hydrogen's electronegativity value is 2.2, oxygen's value is 3.44. When you subtract, it's 1.24, like we met in the photo. That is greater than 0.4. Okay, it's greater than 0.4. Remember the rules, greater than 0.4, but it's less than 1.7. Therefore, it's polar covalent. There are regions of positive and regions of negative separated by some distance there in the water. Methane is CH4. When we look up carbon's electronegativity value, then it comes out at 2.55 is carbon, minus 2.2 for the hydrogen. So you're getting 0.35 there. Now that's less than 0.4. So negligible polarity, we'll take it that it's not polar. Okay, pure covalent, we're going to say. No regions of positive and negative there. And then the MgCl, okay? Magnesium's electronegativity value, when you look it up in your table, is 3.16. Chlorine is, magnesium is 1.31. Chlorine is 3.16. So when you subtract there, you're getting a 1.85 difference, greater than the 1.7. So you know that that's ionic. So if the difference is greater than 1.7, okay, then your bonding is ionic. If it's greater than 0.4 but less than 1.7, then you're going to say that it's polar covalent. There are regions of positives and negatives there now. And if it's less than 0.4, or if it's anything that to note, then you're going to say that it's pure covalent, that there are no regions of positives and negatives there at all in that molecule or compound. Okay. The next thing it asks you to do then in part D of 2008, the question that I'm looking at, is it asks you to draw dot and cross diagrams to show the bonding in magnesium chloride. So that's like what I did in a previous video. Magnesium has 2 electrons in its outer shell. Chlorine has 1, 2, 3, 4, 5, 6, 7. So look, electron goes there. You need to draw another chlorine atom though to accept the second electron. So you're going to have your MgCl2. I did that before. So that was part D of the question. And then finally in part G of that 2008 question, it said to you, it shows you a burette with a thin stream of liquid, okay? And it says the stream of water is deflected towards a positively charged rod, okay? Account for the observation. So all you'd have to say there is, if you've got a burette and you know there's water in it, okay, and you are bringing a positively charged rod to that, account for the observation that the water is deflected towards the rod. So all you would have to say there is that water is polar. So what does that mean? It means there's slightly negatives and slightly positive regions. So a water molecule, okay, the oxygen is slightly negative, the hydrogen is slightly positive. So if you have a positively charged rod, the oxygen atoms of the water would attract towards that and deflect the stream towards the rod, okay? They similarly then said, if you had cyclohexane, which we know is not polar, so there would be no slightly positives or no slightly negatives. And then they said to you, if you brought a positively charged rod, you found no deflection. How would you explain that observation? You would say because there are no polar regions, there's no positives or negatives in the cyclohexane, and therefore the cyclohexane molecules will not attract to a charged rod, be it positive or negative. Okay, so that was the very last part. It was part G of 2008. So I just thought I would do an example there of a question, just to help a small bit with that. So okay, so thank you.